Audio, there we go. All right, calculus one, we are back. So you had that huge lecture, and it really needed to be a huge lecture because I need to introduce you both to the idea of a derivative and a lot of the main patterns and just basic types of derivatives, basic results with derivatives um, that we need to kind of start and get you going. So we looked at quite a few patterns actually. So we talked about what happens when you add two functions together. We talked about what happens with a constant. We talked about the patterns for power functions, sine, cosine, etc. What we want to look at on this lecture then is so basically it's two other more general patterns. So last time we had we had a pattern for power functions, right? That's a pattern based on the function type, right? And then we had a pattern for sine and cosine. We had some other kind of general patterns based on whether you're multiplying by constant, what happens to a constant, what happens to a coefficient, etc. Um, but what we want to look at today is now just two general patterns. So not based on the type of function, but basically based on, what do you call it? Based. So we're going to look at some integrals that based on the structure of, or sorry, integrals, derivatives, based on the structure of the functions that are there. I think I'm going introducing this all the wrong way. Not really, but uh, sorry, a little tired. So based on the basic pattern that we're going to see with the integrals today, let me just, sorry guys, give me a second to get my words better here. Um, so we're going to look at basically patterns for derivatives that apply. Well, what I'm trying to say is it's not that they're patterns that apply to any type of function that's there. So it's not based on the type of function that's there. It's based on sort of, it's based on the construction of the overall function that we have there. So one of the nice things about the pattern today, one of the patterns today especially, is that it applies to a ton of derivatives. So it doesn't apply to certain functions like we were kind of looking at a lot on the last lecture. So a pattern for, like I said, for power functions, or a pattern for this type of function or this type of function. We're going to look at a pattern today that applies to really any type of function, as long as what we're taking the derivative of is set up a certain way. Right? So let me give you an idea of what I'm talking about. And let me leave some room on the board to kind of describe this pattern. But I'm going to start by putting up a problem. A bunch of unnecessarily detailed questions that don't really help you. Let's start with something like this. We're going to look at Exercise 9. So the function that we have is now going to be e to the x cosine x. The x cosine x. And we want to take the derivative of this. So I guess a better way for me to kind of present where we're getting to today is I want you to take a look at this function. And we want to be able to take the derivative of this. Tell me what's maybe different about this compared to the derivatives we saw in the first couple sections. Good. So notice that in the first couple sections, so probably what you're saying is that in the first, we were used to taking maybe the derivative of e to the x or the derivative of cosine x. Or maybe even in the first section, we maybe saw, so let me write this. This is not part of that exercise, but in the first section, we would see something like this, e to the x plus cosine x. They would want the derivative of that. And if I was going to do the derivative of this, so before we do 9, let's do the derivative of this. So let's just kind of rehash what you did in the last section. So if I wanted the derivative of this, what would this be? And I'll give you guys a second to do it. I'll just kind of pace back and forth. So what are you guys getting for the derivative? So the derivative of e to the x is e to the x, and the derivative of cosine x is negative sine x. So that would be my derivative. So what we saw in the last lecture, one of the patterns that we looked at is if you have addition between two functions, you can just take the derivative of each one separately and just run your answer from there. So this is kind of an example of what I'm trying to say is we did looked at one pattern. This is one of the patterns we looked at in the last lecture that applies to any function I could put here, right? So it's telling me that if I add two functions or subtract two functions, I can take the derivative of each individually. What's different about this? So instead of addition, I have multiplication between two functions. So what I'm saying today is if you have multiplication between the two functions, you can't treat it like you did addition. So if you have a different operation between those two functions, then there's a different pattern for how that derivative works out. And it would be nice if you could just take the derivative of each individually, but unfortunately it doesn't work that way. So that is going to be the big difference today. So today we're going to look at derivatives of two functions that instead of being added are either multiplied or divided. And so that'll be the differences. Again, I'm going to give you guys the pattern for how to deal with that, and it'll apply to any functions you could put there as long as they're multiplied together. Then another pattern for division, and that'll apply for any two functions you could put there as long as they're divided. So big thing, the thing I'm going to get at today is if you're, we're going to look at patterns for two different operations or two more operations between functions, multiplication and division. Then after that, we're going to be able to take the derivative of any two functions, whether they're added, subtracted, multiplied, or divided. Because if they're added or subtracted, we know from yesterday or from the last lecture how to handle it. Take the derivative of each individually. And then today I'll tell you how to take the derivative if they're multiplied, take the derivative if they're divided. All right, so what do we do? What is the pattern? So if two functions are multiplied together and I want to take the derivative of that overall function, how do I do that? So actually, let me move this over. On that last lecture, I also gave you that gigantor we call it, I got, I'm so tired. Forgetting words as I'm saying them in my mind, but, um. Give you guys that kind of gigantor quilt or playing board of different patterns for derivatives. So let me give you guys a couple more. So if two functions are multiplied, so they call this the product rule, but I'll, yeah, in the original name. So two functions are multiplied. So one function times another. Pattern for this. So like I said, with addition, it's easy. You just take the derivative of each and you move on, right? Multiplication, it's not as easy. So if I've got two functions that are multiplied, the way I do this is pattern is the derivative of this. Do that, what you do is you take the first function times the derivative of the second function. You add to that second function times the derivative of the first. I've got two functions, f and g, and I take the derivative of it, then my answer is going to be f times g prime plus g times f prime. So not horrible, not hard, but not as straightforward as taking the derivative of two functions that are added together. So for instance, on 9 here, I want the derivative of this. My two functions are e to the x and cosine x. So the first part of this is I'm going to take e to the x, I'm going to take that function and multiply it by the derivative of cosine x. And what is the derivative of cosine x? That's going to be negative sine x. And then I'm going to add to that cosine x, second function, times the derivative of e to the x. And what is the derivative of e to the x? Good. That's e to the x. And then I'm going to do whatever algebraic simplification I can do with that. Notice here we can factor out an e to the x. That's going to leave us with cosine x minus sine x. That is the derivative of e to the x cosine x. Now, honestly, beyond that, the pattern really is as simple as that. Like I said, once you know the pattern, this is going to work every time. So it doesn't matter what functions I have that are being multiplied together. As long as I have two functions multiplied together, you first times the derivative of second, second times the derivative of first, and simplify it from there, and you got it. You got your answer. So let me give you guys a couple to play with that way. Do something like this. I want you to take the derivative of t squared, sorry. Where's the y equals t squared sine of t. Should find y prime on that. So what I'm going to do here, I'm just going to make up some of my own problems because the exercise said this particular section is just not as good as it could be. So let me just make up a couple more. Let's see, we got that, we got that. My own three. Let's do do x equals maybe the square root of x times e to the x. And let's do something like the x cubed natural log of x. So let's kind of get in quite a few. Um, let's put a coefficient in there for fun's sake. Let's do 5 x cubed natural log x. I'm trying to think what are some other. We got those functions. So let's do these. Sorry guys, give me a second just to throw some coefficients in so this isn't so bland. Let's do that here. So for one, let me do this. The square root of x. Um, doesn't matter. But let's make this 2 square roots of x to the x. Yeah, I think that's how these are. So let's make it like this. But like I said, it really is as the product rule, or you got two functions multiplying, taking the derivative, really is as easy as that. You just got to work that pattern. Let's do these one at a time. So go ahead and pause on your side. I'll pause on my side. See if you can get the derivative of t squared sine t. Let's see what you guys got there. So in our pattern is we take the first function. So in your mind, you just got to identify kind of the two functions that are there, right? Which honestly, you'll see, or hopefully you should see for this problem, and you can see for any of these other problems. It honestly isn't hard to identify. I mean, they kind of, when things are multiplied, we kind of, in mathematics, we tend to naturally, or by default, the syntax is we just stick them together, right? So you're literally just going to see these two functions back to back. So you can kind of see what they are. The first one is t squared, the second one is sine t. So we're going to take the first and multiply by the derivative of the second. And what did you guys get for the derivative of sine? That's going to be cosine. Then we got to take the second, which is the sine, and multiply by the derivative of t squared. And what's the derivative of t squared? That's going to be 2t. Notice that this really can't simplify it much more, right? I mean, that is what it is. So t squared cosine t plus 2t sine t. That is your derivative. So no real issues there. So let's pause again. Actually, I'll give you guys time. I actually want you to work through both of these. So for the third and the fourth one that I've given here, go ahead and pause on your side, I'll pause on my side. Take your time to work through both of them and find their derivative. Let's see what y'all are getting on these. So on 3, the first function is that 2 square roots of x. Second is the e to the x. You're dealing with this. Sure, what you guys did is remember this, think of this as two squareds, sorry, not squareds. It's two x to the 1/2 power. To the x. All right, so f prime. Gonna have two x to the 1/2 or 2 squareds of x times the derivative of e to the x. And what's the derivative of e to the x? That's e to the x. And plus, now you gotta do the derivative of 2x to the 1/2. And what did you guys get there? Good. So 1/2 times 2 is a 1, and then you drop the power by 1. So this is going to be x to the negative 1/2 e to the x. And we can factor out an e to the x there. So you end up with 2 square roots of x plus, that's really 1 over the square root of x. Actually, quite a few different ways you could write that if you want to kind of do all different versions of simplest form that they've shown you in classes so far, but that works well enough. That's my derivative on 3. And 4 is an interesting one. So again, my first function is 5x cubed, my second is natural log of x. So y prime, take the first function, 5x cubed, and do multiply by the derivative of natural log of x. And what is the derivative of natural log of x? Good, that's 1 over x. And plus, now we're gonna do natural log of x times the derivative of 5x cubed. And what's the derivative of 5x cubed? So you should have got 15x squared there. Now this 1 over x obviously kind of simplifies this. So we end up with 5x squared plus 15x squared natural log of x. And then again, you don't have to, but there's a little bit of simplifying we can do there with common factors. So we can factor out 5x squared. That leaves us with 1 plus 3 natural log of x. That's pretty nice little form there. So that would be my derivative. So when I say the product rule or pattern is that easy, it really is that easy. Even let's look at something like, so there is one problem, a couple problems in this section that I did like out of their exercise set. Here. Yeah, books.
Oh, the bathroom.
Report. Something like, let's alter one of their problems. Let's do something like So here h secant x over x cubed. And they want you to take the derivative of this. Now notice here that we have division between these two. And there is, so we're gonna go over, there is a quotient rule, there is a way to deal with division. But notice that at least for this, we don't have to. So we're gonna, that's kind of where I want to bridge into. We're gonna show you, I'm gonna show you some problems where you're not gonna be able to just sort of get rid of this division. But we do know, and from what you guys have already seen, this divided by x cubed, how could I rewrite that in terms of powers? I could rewrite this as secant x times x to the negative 3 power. And because I can rewrite it as x to the negative 3 power, then now that's multiplication and I can use the product rule. So you actually see there's a lot of, not a lot of, well, yeah, there's quite a few situations. There's a lot of situations where you can, even though it looks like something else, you can rewrite it in a way that gives you multiplication instead. And if you can, honestly, that's going to be that's going to give you the least amount of work in finding the derivative. It's going to be your quickest, most efficient, best bet at finding the derivative. Good. So on this one, even though you see division, I can rewrite it as times x to the negative 3, and then I can do the product rule. So I'll have you guys do that. So go ahead and pause on your side. I'll pause on my side. Go ahead and work out the product rule. All right. So easy enough. The first time through, it's secant x times the derivative of x to the negative 3. And what is the derivative of x to the negative 3? So you should have got there. That's going to be negative 3 x to the negative 4 power. Then the second time through, we're going to do x to the negative 3 and multiply it by the derivative of secant x. And what's the derivative of secant x? That's secant x tangent x. Then again, a little bit of common factors and some simplifying we can do there. It looks like we can factor out a secant x from everything. And actually, let's see, actually, what's the best way to write this? Well, yes, you can factor out x to the negative 3 as well. I can show this in a couple lines only because the Cal 1 class, so you guys have been through algebra, you've been through pre-cal. I know you're good with some of these algebra skills, but I do want to make sure you see this. So that leaves me a negative 3 x to the negative 1 here. It leaves me a tangent x here. I'm going to put the tangent x first because it's positive. Tangent x minus 3 x to the negative 1. Then I'm just going to convert these x to the negative powers into their fraction equivalents. So it'll be secant x over x cubed times tangent x minus 3 over x. That's our derivative. Honestly, kind of, again, our function starts out as secant x over x cubed, and you take the derivative. It seems kind of benign, like it should, but you kind of come up with one. Notice that secant and cosecant are always interesting. We talked about it a little bit last time, that the derivatives of secant and cosecant are the same function multiplied by another function, right? Kind of expand and add another function there. So you kind of see the same thing here. The derivative of secant x over x cubed is that times a whole nother piece, tangent x minus 3 over x. All right, good. One more problem I want to look at as far as the product. I was looking at the product rule. Just to give you guys, well, not to give you too much foreshadowing, but just give you a nice caution. Um, actually, this. Well, okay, maybe a couple more we need to look at. Let's look at something like this. So this is actually 33, the exercises. And my function is x times no, that's actually I'm actually good without this one. Let's look at another one. So look at something like this is actually number 7. Exercises. This is the square root of t times one minus. Spice this up. So I'll call this my 6. Let's change the numbers here a little. Let's do 3 minus maybe 4t squared, something like that. Like 1%. So you get something like this, and they're going to ask you to find the derivative. Now, we could just play this out like all the others. So you could take this times the derivative of this plus second times the derivative of the first. I do want you to notice though, so if you look back at all these other examples I gave you, you kind of had like going even go all the way back to 9. You had 2 different types of functions. So we have exponential trig function, have power function, trig function, have radical function, exponential, etc. Power function, natural log function. Then I would have 2 different types of functions. But notice that these, so this is a radical and this is a polynomial, but we know we can rewrite this as t to the 1/2 power. So let me write that. Let me note that. So this is, think of it as t to the 1/2. Once I have it written this way, are these really 2 different types of functions? Not necessarily, they're both power functions. And better question than that, could I multiply through on this? Yeah. So notice on this one, I can actually multiply through. Now, again, I couldn't have done that on any of the other ones. Because they're different types of functions, I can't multiply e to the x with cosine x. I can't multiply t squared with sine t. Can't multiply square root of x with an e to the x, etc. Can't multiply an x cubed with a natural log of x. But I can multiply t to the 1/2 with this. So my point on this one is even though they presented as 2 different functions multiplied, in this case I can actually distribute and multiply them through. If you look at the result there, so if I do t to the 1/2 multiplied through, that's going to be 3t to the 1/2 minus 4t to the 2.5, which is 5/2. Notice that now I want to take the derivative of this. This is just two power functions subtracted. So I can take the derivative of each individually and go. So what I'm saying is, even though you can do the product pattern with this, if you realize that you can actually multiply through, this is easier to do. So it is easier to actually multiply through and take the derivative from there, because then you don't have to do product rule. You're just doing the addition rule. You're just doing the derivative of each and just putting it down and going forward. So look out for that. They are going to give you some problems that you can actually multiply through and then just do your derivative normally, just to do the derivative of each piece. And if you can do that, that's much easier. So we can on this one. So go ahead and take a minute, pause on your side, I'll pause on my side. This is easy peasy. Go ahead and take a derivative, or take the derivative from here. All right, sweet. So multiply by 1/2 here, so you're gonna get 3/2 e to the negative 1/2. Then we're gonna multiply by 5/2 here, so you're gonna get actually minus, so you should have got minus 10. 5 is 20, and 20 divided by 2 is 10. And it's gonna be t 5/2 minus 1 is 3/2. And if you want, you could write this as t to the 1/2 on the bottom. You could turn things into square roots. But either way, this is our answer, actually. Notice again how easy that was. Because if we'd done it the other way, you were going to have to, one, do your product rule, write it out, square root of t times the derivative of this, and then plus vice versa. And then you're going to have to do a bunch of algebra to simplify that. So this just makes it a good bit quicker. But only when you can. So we could do it on this one. We couldn't do it with any of the problems before this. Those, basically it's if the function types match. Okay. That's the product rule. Easy enough. What about when I have two functions divided and I can't kind of simplify it? Like on 5, we had two functions divided, but I could rewrite it or simplify it as two functions multiplied. But what about when I can't? For instance, let me find one for you guys. But yeah, again, I'm not even going to worry about their problems. So let's just keep, for instance, let's say I had something like maybe 4x cubed divided by cosine of x. So in this case, I don't have any slick algebra. I mean, technically I could write this as cosine of cosine to the negative 1x, but that doesn't convert it into something I can take the derivative of. So there's no slick algebra that basically turns this into multiplication, allows me to do what we did on 5. Here we just gotta kind of, we're stuck with, really have one function, 4x cubed divided by another function. So when you're in a situation like that, that means we can't use the product rule. So we need a rule or a pattern, or they needed to, again, these mathematicians, Newton, Leibniz, and people who came after, they needed to study or prove in general, what's the pattern for when I have one function divided by another. So what they found is if you have one function divided by another, if I get this right, I want to take the derivative of that. And what I get, I'm going to take the second function, the bottom function, multiply it by the derivative of the first, minus first times the derivative of the second. You're gonna divide this all by the second function, the bottom function squared. Now this, obviously the quotient rule, the pattern for the quotient rule, obviously this is not as simple as the product rule. It's kind of one of these, it's unfortunately necessary. It kind of is what it is. It's kind of like the quadratic formula. It's not the greatest thing to remember, but it is the pattern and it does get the job done. It gets you the answer, right? So the same thing here. Um, so again, we just want to go through and practice using the quotient rule, something like this, so that we can get the derivative. So for instance here, if I want the derivative, then what the quotient rule says is I want to take the bottom, I want to multiply it by the derivative of the top. What's the derivative of the top? As a second on that. So the derivative of the top, 3 times 4 is 12, so that's going to be times 12x squared. Then I'm going to subtract, and you're basically just going to reverse your roles. So now you're going to take top, 4x cubed, multiply it by the derivative of the bottom. What's the derivative of the bottom? The derivative of cosine is negative sine. Then I'm going to divide this all by the bottom squared. So in this case, cosine squared x. Then you're just going to do whatever simplifying you may or may not be able to do, but just whatever simplifying you can see that you can do. So for instance, what I see here, obviously negative times negative is a positive. Don't really have much of a common factor here. Technically, we have 4x squared as a common factor, so I don't think this will change or simplify much about how we write it, but we'll take 4x squared out, and that leaves me, let's see, 3x cosine x and plus, oh, sorry, not 3x, 3. Leaves me 3 cosine x plus, it's like x sine of x divided by cosine squared x. I don't think there's much other simplifying we can do with this. So that is our answer. The derivative of 4x cubed over cosine x is 4x squared, 3 cosine x plus x sine x all over cosine squared x. So by nature, necessarily kind of complex. But again, it is what it is. This is the pattern, this is the derivative, gets the job done. So as long as you have two things that are divided by each other that you truly can't rewrite as a product, again, not the greatest thing to remember, but it's true and it gets the job done. That's the derivative. So let's do a couple of these. See if there's any good ones out of the book. Otherwise, we'll just make up my own series. What I would want. let's do these kind of one at a time, but let's try something like this. So I want you to find the derivative of this. So see if you can play that same pattern out. And then see if you can kind of work the algebra there to simplify things. And but even if not, at least see that you can play this pattern out. Go ahead and pause on your side. I'll pause on my side. All right, let's see what y'all are getting then. All right, so we start out, we take the bottom function. X squared plus 4x. And we multiply it by the derivative of the top. And what's the derivative of natural log of x? That's 1 over x. Then we add natural log of x times the derivative of 3x squared plus 4x. And what did you get for the 3x squared plus 4x? The derivative there is 6x plus 4. Then we're going to divide this all by 3x squared plus 4x squared. Okay. So as far as taking the derivative, you've done the thing. Now you see there is a bunch of mess here, and we're going to try to simplify that mess. So the rest of this is not, you've done the thing, you've done the derivative. The rest of this is just algebra and simplifying. And again, you hit something like this, and honestly, this is again another situation where you just may not know where to go. Thing is, that's fine. Find what you can do. Kind of treat it like trial and error. Find what you can do, work a step, work some things that you can do, and start seeing if there's more algebra, if there's more simplifying, the more canceling of common factors. There's just more work that you can kind of keep doing from there. So what I see here, there's a couple things. So this 1 over x times the 3x squared plus 4x, that essentially divides an x off of each of those pieces. So you're going to end up with 3x plus 4. Then that's plus this 6x plus 4 times the natural log of x. And I could distribute the natural log of x if I want, but I'm just going to get natural log of x in front of each of these. So that doesn't really simplify anything there. So I end up with a top that is just a bunch of separate pieces that I can't really combine. The bottom then x plus 4x squared. So you can go ahead and distribute that out. Oftentimes what they do, at least in the book, as far as the homework answers, they leave it with it squared like this. So basically, if squaring it doesn't give you something that you can then cancel out with the top, then you don't want to, they're non-sadistic enough that they're not going to make you actually go through doing 3x squared plus 4x times 3x squared plus 4x. In terms of algebraic simplifying, this is actually about as simple as it gets. Looks horrible, and that's okay. Some things are by nature complex. Our universe is complex. There are things that just don't simplify down. So this is one of them. All right, so something like that. We may not do too many of these just because there's not a bunch of funny revelational things that happen with these. It's just kind of, like I said, it's by nature complex, and so you end up with complex things. Let's see. See if there's any of these that have any more interesting elements. Yeah, let's maybe do this one just because there is some. So this is I think it's exercise 15 out of this section. So this is going to be y equals sine x over e to the x. Want to go ahead and find the derivative. But same pattern. So again, notice that I can't really simplify much of anything about this. Although that's the reason let's just kind of work through. So, so I'll have you guys work this through. So, but same pattern, and two different types of functions that we can't really convert into multiplication here. Um, anyways, so go ahead, my man. So same pattern, run it through, trust it, and then the bigger thing is see if you can do some simplifying in the end. So pause on your side, I'll pause on my side. Go ahead and see if you can work all the way through this derivative. All right, let's see how y'all got through this. So my pattern for quotients for division here. So I'm going to take the bottom, multiply by the cos or the derivative of the top. Derivative of sine is cosine. And subtract top sine times the derivative of the bottom. But what's the derivative of e to the x? It's e to the x. And we're going to divide by e to the x squared. Now, before we get all excited about squaring that thing on the bottom, notice we have a common factor on the top, which is e to the x. So we can factor out e to the x on the top. That's, let me actually give a little more space here. That gives cosine x minus sine x. E to the x squared. And so notice that then basically an e to the x in the top to cancel out with one of your e to the x's that is being multiplied in the bottom. So I literally can cancel this out with one of these, and I'm left with cosine x minus sine x for e to the x. Good. So the derivative of sine of the x over e to the x is cosine x minus sine x over e to the x. So kind of, I think there's an interesting pattern to there, especially visually. Good. Okay. Easy enough. All right, then what I want to do is I want to look at it. So I want to look at a couple problems. We'll do a couple problems here that are just so just rehashing a couple of the types of the problems that you guys saw in the last lecture. So we'll find the equation of a tangent line and we'll figure out when a function has a horizontal tangent line. But then I also want to get to one other topic here that isn't about the product rule or quotient rule, but just one other topic that they kind of throw into this section. So, all right, but all right. So for these, I do need at least applied problem. I do need very useful. All right, so let's find. Let's start with, this is 69. Um, f of x equals, so the function they give me is f of x equals x over x plus 4. Give me the point -5, 5, I believe. Sure I got that right, yeah. -5, 5. And what they want here is they want you to find the equation of the tangent line. So remember, if they're asking for the equation of the tangent line, find the equation, we'll need this, or to write the equation, we'll need the slope and a point. So we already got the point, we just need the slope. The slope of the tangent is the derivative. So kind of, again, just knowing those, reminding yourself of that, tells you where to go with this problem. You got to find the derivative and plug the x value in so you get the slope at that point. Once you have that, you can create tangent line. So let's do this in pieces. Your first job is to find the derivative here. Notice this is two functions divided. I can't really simplify it either. It looks like you're going to need the quotient rule. Okay. But that's something, as you do these problems, you got to kind of look at that and figure out for yourself, okay, which of these patterns am I using here? So pause on your side, I'll pause on my side. Go ahead and see if you can find the derivative of that. All right, let's see what you got here. So I need the quotient rule on here. So the quotient rule says I take the bottom, multiply by the derivative of the top, but what's the derivative of x? That's just the 1, so it's just gonna be x plus 4. Then I'm gonna subtract the top times the derivative of the bottom. What's the derivative of the bottom? That's also gonna be 1. So basically minus 1 times x, or just minus x. This is all over x plus 4 squared. Now notice on the top, there is some nice canceling I can get there. So the derivative here ends up being 4 over x plus 4 squared. So this will tell me the slope at each x value, at each point on the original. So then to find the slope at -5, all I got to do is plug it in. That's going to be 4 over -5 plus 4 squared. And what is that going to give you? Should work that out for a second. -4 plus 1 is, or plus 4 is a -1. -1 squared is a 1. So this is just going to be 4. That is my slope. So I have a slope, I have a point, a slope of the tangent line, a point that it goes through. So now I should be able to write an equation for that tangent line. So I'll have you practice. We did this once on the previous lecture, but I'll just have you practice through that. And you've done this a ton in previous algebra classes. So go ahead and pause on your side. I'll pause on my side. Just see if you can put that equation together. Right, you guys couldn't hear that because there was some glitch with the recording. But slope is 4. There's your point. So y minus the y value equals the slope times x, and then minus a -5 is +5. And work out the algebra from there, and it's y equals 4x plus 25. Right, easy enough. And then there's the type of problem where they ask you for where you have a horizontal tangent line. Let's make sure this. I should. Let's look at this. 82. So the function is e to the x sinus. In fact, I'm pretty sure we found the derivative of this earlier, but let's just do it again. But what they're asking for here is where is the tangent line horizontal? They're gonna ask you a question like this. Again, to remind you guys from what we saw last time. Let's see how much of this you guys can see. Again, whenever they say tangent line, tangent means derivative. And then the derivative tells you the slope of the tangent line. For a horizontal line, a flat line, what's the slope? Slope or the derivative equals 0. Again, this kind of tells you how to do this problem. You again need to find the derivative. You need to find where that derivative equals 0. And they do give you a sort of domain restriction or just a range that we're looking in. We're looking from 0 to pi. For an answer from 0 to pi. But yeah, we'll need to take the derivative, then set it equal to 0. Figure out where that is. So again, we did this last time. I want to see if you could play that out. So go ahead and find your derivative and then set it equal to 0 and see if you can figure that out from there. See how you made it through this. What you got? So f prime, then notice these are two functions multiplied, so I'm going to use the product rule. So it's going to be first times the derivative of the second, so e to the x times cosine x, plus the second times the derivative of the first. What's the derivative of e to the x? That is also e to the x, so I'm just going to go ahead and write it, but rearrange with the e to the x at the front, because again, I think we did this earlier, like we saw earlier. Factor out e to the x, and you get e to the x cosine x plus sine x. Yes. That's my derivative. Now I want to know when this derivative equals 0. So a bit like I was talking about in the last lecture, once you get to this part, you are on the hook for all the types of equation solving you've ever seen. And don't think of that as a negative thing or kind of like, oh crap, am I going to remember all that? I promise you, you actually got this. You've passed and started to master, college algebra, pre-cal. have these tools. So I set this equal to 0. What that means is each of these, I obviously want to figure out where each of these factors equals 0. I want to figure out two things. Figure out e to the x equals 0. And I want to figure out this equation, cosine x plus sine x 0. So e to the x equals 0. What would you get there? Or how would you solve this? And to solve this, one way to solve this is you essentially turn this into its log form. So this is going to be the natural log of 0 equals x. But can you take the natural log of 0? Good. That's impossible. So if you think about it, the e to the x function, if you think about the graph of it, it actually has a horizontal asymptote at 0. So literally, it never reaches 0. So this is impossible. Now in this one, we want to solve this. So what I'm going to do is I'm going to subtract sine x. This goes back to your pre-calc class. You had the not only the section, but you had that little bit of time where you're sitting there solving equations with trig ratios. This one doesn't have any special factoring or that kind of gets us to an answer. But what it does say is that we're looking for angles where cosine equals negative sine. Or you can think about it even going back to the original equation. We basically want cosine and sine to match, but to be opposite signs. So we need an angle. So, and I'm sorry, when I'm saying all this, I'm saying we need to find one angle where cosine and sine match, but they're opposite signs, so that when you add them together, you get 0. So this is where you got to go back to your unit circle. So the interesting thing about this is actually there's nothing on this, unfortunately, that you can throw in a calculator and say solve. This is where you really need to think back to what you know from your pre-calc class. And one of the biggest tools you had in your pre-calc class was unit circle. Honestly, your biggest tools in the pre-calc class were a unit circle, the law of sines, law of cosines, and your trig identities. But so let's think back on the unit circle. I need an angle where the cosine and sine match their opposite signs. So think about just in any quadrant, what is the angle where the cosine and sine match each other? So in any quadrant, the 45-degree angle is the only place where the cosine and sine match each other. So again, if you want, pause the video and just kind of bring up a unit circle, kind of look at this just to kind of confirm what I'm saying, but also to get yourself to see the idea we're getting at. So now that it's unpaused, no, but in every quadrant, the 45-degree angle is the only place where the cosine and sine match, at least in value. The difference is the signs usually. So in the first quadrant, they're both square root of 2 over 2, cosine and sine of 45 degrees. In the second quadrant, one is positive, one is negative. So that's the angle that we're looking for, because again, they wanted us to look for angles from 0 to pi. So just in either first or second quadrant. So in the second quadrant, the 45-degree angle, which angle is that? That's actually 135 degrees, or in radians, you could write it as 3 pi over 4. I will say in a calculus class, unless they ask for angles in degrees, your answers are always radians. Radians is the exact measure. So the answer here, and again, so the surprising thing about this, there's no like algebraic technique that solves this. Actually, the only way you can solve this is look at the unit circle and find your answer. But solution here, they want to know where's the tangent line horizontal. It's horizontal at x of 3 pi over 4. If they want an ordered pair, then you just go ahead and plug this in back to your original function. All right, so again, pretty much, well, maybe not in every section, but pretty much in every section, we can kind of sort of redo these problems, right? So every time you learn a new way to find a derivative that works on some other functions, you can find the equation of a tangent line and you can find where the tangent line is horizontal. So you're going to probably see these a little bit in every section. All right, so then, like I said, there's one final topic that they sort of add into this section, and it's the idea of a second derivative. So we've been starting with a function. And when you take a derivative, we've been taking a derivative of it. So we start with a function and we take a derivative. We haven't had a reason to sort of call it anything other than derivative. But in some ways you can, so I'm gonna call this thing that we're doing after the derivative, I'm gonna call it the first derivative. So the idea here is, like any of these functions I've worked with. So I have the original function and I find the first derivative. Now the question is, what if whatever I get as results, first question is, could I take a derivative of that? So if you think about that, well, sure. I mean, when I take a derivative of a function, I get another function. Could I take a derivative of that? Sure. Yeah, it's another function. I can run the derivative again and get another answer, get another function out of that. Well, since I'm getting another function out of it, so they start to sort of count derivatives. So if you're going to do this chain where you start with a function and take a derivative, and then take a derivative again and take a derivative again, and you may ask, well, why would I want to do that? We'll see. So after we're done with this midterm and just knowing how to deal with derivatives, we'll look at some applications and you'll kind of see why you might want to take more than one derivative. But again, so you have this chain of, you start with a function, you take a derivative, then you take a derivative again, and we might just want to basically keep track of that process. So when you have a function and you take the derivative, call that the first derivative. If you take the derivative again, then we're just counting. So then when we take the derivative again, that's going to be called the second derivative of that original function. And you could keep doing this. There could be a third derivative, a fourth derivative, fifth derivative. We could take the derivative of this function as many times as we want. So they'll start using this vocabulary, they'll start using these words just to count, keep track of the number of derivatives you've taken of sort of some original function. So what we're gonna do is we're gonna take some original function. What you'll see in this section is they'll ask you to take the second derivative of these functions. So you're gonna take some original function and they're gonna want the second derivative, which means you're gonna have to take the derivative once. And then whatever you get, you're gonna have to take the derivative of that again. So let's work a couple problems like that. Here again, let's see what they have. I'll probably use some of their problems. Let's start with something like this is 98 out of their exercises. 4x to the fifth minus 2x cubed. I was trying to memorize it. So minus 2x cubed plus 5x squared. So we're starting out with just some polynomial. They're going to want you to find the second derivative of this function. So you're going to need to figure out the first derivative. And then once you've got that, you're going to take whatever that is, you're going to take the derivative of that, and that'll be your second derivative. But notice that this is easy enough. Again, this is a polynomial. It's just a bunch of power functions being added or subtracted. So again, you want to think back to your patterns. To get the derivative, you're just going to do the derivative of each separate piece. So again, if you're adding or subtracting your functions together, just do the derivative of each piece. So you can imagine you'll end up following that same pattern the second time through. So this I'm saying you can already do this. You actually don't need me to even do an example or really teach you how to do it. You can already do this. You can find the second derivative. Just take the first derivative and whatever you get, then take the second derivative. So go ahead and pause on your side. I'll pause on my side. Go ahead and do that really quick. All right, so let's see, for the first derivative. What did y'all get? So this part, 5 times 4, that should be 20x to the fourth. 3 times 2, that should be minus 6x squared. 2 times 5, that should be plus 10x. So then my second derivative is going to be the derivative of this. So then you just want to run that pattern through again. So 4 times 20, 80. So 80x cubed times 6 is 12. So minus 12x. Then the derivative of 10x is just 10. There you go. That's your second derivative. Well, that's all. You're just taking the derivative 2 times. Let's look at maybe one more. Something like 103. Function is x times the sine of x. I want you to find the second derivative. So first time around, so notice, so in the last problem, we were using just the addition property or the addition pattern, but you were adding and subtracting so you could take the derivatives of each piece. Here, what's my operation between the functions? Multiplication, which means I need to use the product rule to get my derivative. The first time through, I'm gonna do the product rule just like we've been doing. So it's gonna be x times the derivative of sine x. What's the derivative of sine x? Cosine x, and then plus sine x times the derivative of x. And what's the derivative of x? That's just a 1. So this should just be plus sine x. That's my first derivative. Now for the second derivative, now notice that I'm going to have to take the derivative of this part, which is going to be the product rule because I have x times cosine of x, but I'm also just going to then plus just whatever the derivative of sine x is. So we have a little bit of 2 little patterns that we got to run there. And again, it's just looking at your result and kind of analyzing what do I need there? What patterns do I need to get the derivative? Good. Something you should easily be able to do. So go ahead and pause on your side. I'll pause on my side. See if you can run this second derivative here. All right, see what you got. So on the x cosine x, so first of all, I'm gonna do product rule with that. So that's gonna be x times the derivative of cosine x. And what's the derivative of cosine x? That's negative sine. And plus, so we're not even at the sine x yet. We're still doing product rule, plus cosine x times the derivative of x. And what's the derivative of x? That's 1. Plus cosine x. And then we're gonna plus the derivative of sine x. And what's the derivative of sine x? It's cosine x. So now notice that quite accidentally, I mean, there's no great mathematics that sort of necessitated that this was going to happen, but you happen to have some like terms here. So we can combine this into negative x sine of x plus 2 cosine x. So the second derivative of x sine of x is negative x sine of x plus 2 cosine of x. Easy enough. And really, I mean, so again, they're introducing this in this section to say, hey, this is how we label it. This is how we talk about it. But you can start with a function, take a derivative, and then take a derivative of that derivative. And we call that the second derivative. And we can do third and we can do fourth. So this is now something you can play with and do. And we could do another problem, but it would be the same play, just maybe in different patterns for your derivatives. But we could do one where with the quotient rule, but honestly, algebraically it'll take a second. So I'll kind of, I mean, you guys will have to do it for your homework, but you guys get the idea from here. So for time's sake, I'm gonna leave it off. But otherwise, that is it. That's product rule, quotient rule. And then now we can do second, third, however many derivatives we want. So there's one other general pattern with derivatives that, so we've looked at several general patterns now. So like I was saying at the beginning, what I was trying to say at the beginning of this lecture is we've seen patterns for certain types of functions, derivatives for certain types of functions. But in terms of general patterns that apply to any combination of those functions, basically I've seen a pattern for adding and subtracting functions, which is you just take the derivative of each separately. And now we've seen a pattern for if we multiply functions and divide functions. So those are patterns based on operations between the functions. There's one more pattern of, in for general, one more general pattern for if we kind of have two functions present that we're trying to take the derivative of, two or more. And we'll look at that in the next lecture over 3.4. And then the surprising thing is that'll actually handle our patterns for derivatives, pretty much anything that we can look at. Not quite everything, but pretty much anything. So this next lecture will actually take care of everything you need, both for chapter 3 for your homework for this week, but it will also take care of everything we need as far as derivatives. So next week, we'll actually be looking at taking the midterm because now we have the skills to take all the limits and all the derivatives that we want to be able to take. So that's what's coming, but I'll see you guys for the next lecture.